Now let's continue further, look into the various parametric statistical hypothesis tests available for machine learning. The parametric hypothesis testing is a statistical hypothesis test which assumes that the sampling distribution is known and depends on a fixed set of parameters. The parametric test can perform well with skewed as well as non-normal distributions. The parametric test can perform well when the spread of each group is different, and parametric hypothesis testing uses higher statistical power, has got a higher statistical power. So usually this parametric hypothesis testing is done with the samples whose distribution is known, and instead of the whole sample, we can just represent the sample with a few parameters. Like if the sample is known to be normally distributed, then this whole millions of elements of the sample can be just represented by two parameters, mean and the variance. So when you are trying to compare two samples, and if you know that the two samples have same distribution, then it becomes easier. Just compare means and the variance of the two samples. If they are same, you have one situation. If they are different, you have another situation. So basically there are four parametric statistical hypothesis tests which are important in machine learning world. They are students t-test, paired students t-test, analysis of variance test, very famous as ANOVA, and repeated measures ANOVA test. So let's look one by one. Students t-test. So this test whether the means of two independent samples are significantly different. So we have two samples and the two samples are independent. And we just want to see whether the two means are same or different. Of course, we do need to observe some assumptions. So the assumptions are, of course, when you're doing any hypothesis test, we would expect the samples to be IID, independent and identically distributed. And then the samples are supposed to be normally distributed, and each sample should have same variance. The interpretation, the null hypothesis says that the means of the two samples are equal, and the alternative hypothesis says that they are not equal. That means null hypothesis say mu1 equal to mu2, whereas alternative hypothesis say mu1 not equal to mu2. So the Python function available for students t-test is t-test underscore ind for individual. That means we are talking about two independent samples. IND stands for independent, data 1 and data 2. So when this function is run, it returns two values. One, the statistics about the test performed, and a p-value. This p-value is important for our hypothesis. If p-value is less than equal to 5%, then the null hypothesis is rejected, which means that the means of the two samples are not equal. If p-value is greater than 5%, yes, the null hypothesis cannot be rejected, which means that the means of the two samples are equal. So we can look at the p-value and decide whether the two samples are similar or not. Then comes a paired student t-test. So in the previous case, we were talking about two independent samples. That means we were maybe working on student scores of two different classes. And we are trying to see whether the distribution of the two different class students is same or not. But in this case, we are talking about the same class, but two different exam scores are being used. Maybe the mid exam scores and the final exam scores. The same students appear in both the samples, so they are paired. So this is going to verify whether two samples of the same people, are they significantly same or different? The means of these two are same or different is what we are trying to test. So that is done through paired students t-test. Again, assumptions: IID normally distributed, having same variance. Yes, they are required. One more thing is the observations across each sample are paired. That means the number of students which are there in one sample, the same number of students are there in the other sample. The students who are there in one sample, same students are there in the other sample also, so that one particular student's mid marks in one sample, you get a final marks in another sample. So there is pair. So this usually is required if we want to compare how the class is performing from time to time. So how the class performed in the mid exam, how the class performed in the final exam, or month by month, is there any progress or not? So if you are trying to do such test, yes, we need to do paired student t-test. And the interpretation here is the null hypothesis claim that the means of the samples are equal, and the alternative hypothesis claims that the samples have different mean. Now the function available in Python is t-test underscore rel for relative. That means you are talking about relatively on the same set of people. So data 1, data 2 are two things which are passed on to this, and that produces two outputs, stat and p. P value is used to either reject null hypothesis or not to reject null hypothesis. If value of p is less than equal to 5%, then null hypothesis is rejected, which means H1 is accepted, which means that means of the samples are not equal. If p value of this test happens to be greater than 5%, then we cannot reject the null hypothesis. Therefore, the claim that means of the samples are equal is upheld. So that's a paired students t-test. Then we have analysis of variance test, very famous as ANOVA test. Here, the test is done whether the means of two or more independent samples are significantly different. So earlier we were worried about only two samples. Now we are talking of two or more samples. So we are now having chance of comparing even more than two samples at the same time. And assumptions that each sample are independent and identically distributed, each sample are normally distributed, each sample have same variance. Interpretation: the null hypothesis claims that the means of each sample is equal, whereas alternative hypothesis claims that at least one of the means is not equal to the others. Yes, we have a function f underscore one way in the Python, and we can pass on two or more data, two or more samples into this function, and we get stat and p as the outputs. P is the one which is useful in deciding whether null hypothesis is rejected or not rejected. If p value is less than or equal to 5%, it is rejecting the null hypothesis, which means it upholds alternative hypothesis, say that at least one mean is different from others. Whereas if p value is greater than 5%, then we cannot reject the null hypothesis, which means that all the means are equal. That means mu1 equal to mu2 equal to mu3 equal to and so on. So that's ANOVA. A similar thing which is worked on paired samples. Yeah. Now instead of talking about student score in mid-exam and final exam, now you can talk about quarter exam, first quarter exam, mid-exam, third quarter exam, and final exam. Four results we have, 4 marks we have for the same class. So they are paired. That because they are talking about same set of students, therefore it's trying to see whether the performance of the class is similar in all the 4 tests or not. So here we have paired samples, 2 or more paired samples, and we are trying to find whether means of these are significantly different or not. So assumptions, yes, of course, IID is a must, otherwise no statistical work can be done. Then we are assuming that all the samples are normally distributed, also assuming that all the samples have same variance, and observations across each sample are paired. Yeah, there is connectivity from one sample to other sample, because it's something like different exam results of the same class. So interpretation, the null hypothesis claims that the means of the samples are equal. Alternative hypothesis claims that at least one of the means is different from others. So this, as of now, Python has no direct function available for testing this measured repeated measures ANOVA test, but other platforms like R and all that do have. And whatever, we can always find a p-value for this test, and if p-value is less than equal to 5%, we can reject the null hypothesis and claim that at least one of the means of these samples is different from others. If p-value is greater than 5%, then we cannot reject the null hypothesis, which means that means of all the samples are equal. That means mu1 equal to mu2 equal to mu3 equal to mu4 and so on. So that's it for parametric methods. So see you soon for non-parametric methods.